Hi everybody and welcome back to a lecture series on Calculus 3. This is going to unfortunately have to be a bit of a briefer video today. I'm just going to do a read through on the notes that I've written and posted. Sorry, I am currently setting up for my classes. I just started at Indian River State College and I'm a little bit pressed for time. I would have liked to have gotten this video out a week ago, but my apologies. So, first of all, the synopsis, little TLDR. We're going to be talking about equations for lines and planes. So, given a certain point and a direction, we could define a line through it parametrically in this way, where the A, B, and C indicate the direction, and this time parameter, or this t value, tells us sort of how far we are before or behind some starting point along the line. If we are A, B, or C are all mutually not zero, then we could solve for t in each case and set them equal to each other. This form of the line is actually called the symmetric form of the line, is actually something we could get if we were in 2 dimensions. Try this out. You could solve this and get it into the normal form that we're used to, and what would the meaning of the slope be? So we could also, in the same way that in R2, 2 points determine a line, that's also true in R3. So given 2 points, well, we could define a line. Let's just let the vector directed along their displacement be equal to v, and then you just proceed as you did before. Notice that the condition that A, B, or C is not zero is the same as saying that the starting and ending coordinates are distinct. Finally, we're going to learn for lines here how to discern the distance between a point and a line. And that's going to be this expression involving the cross product here. For the first time, we have a second page, because I couldn't fit all of these equations onto one page. The normal vector, we're talking about equations now for planes instead of lines. And the normal vector to a plane is the vector that points straight out from it, right? If you pick a direction, there is a plane and a point. Then there is a plane through that point, containing that point, with a 90-degree vector pointed out of it in a certain direction. So there's an equation that goes along with that. We'll see why this equation has this form. And we'll note that we could also rearrange things to get it into a general form that looks like ax plus by plus cz plus some d is equal to 0. Now we could also look at 2 vectors that are not parallel or anti-parallel with one another and find an equation for the plane that contains them both. That's going to involve finding their cross product to find the normal vector to the plane. Remember, the cross product of 2 vectors is mutually orthogonal to both of them. Finally, if we have 3 points, well, we could just let I'll write this in blue. Let u be equal to one displacement vector, let v be equal to the other. Doesn't really matter which ones you pick. You get a different form, but an equivalent plane. And then we could just repeat the steps before to find out the equation for the plane. Now, just like we can find the angle between 2 lines, or 2 vectors, using the dot product, we can also note that the angle between the 2 normals is equal to the angle between the planes. There's a good, easy geometric reason why that's the case. And then using the formula for the dot product, we could find something involving the lengths of the normals and the magnitude of their dot product equal to the cosine of theta. If we wanted theta, we take the inverse cosine. Finally, we'll look at one more distance problem. What is the distance between a point and a plane? And we'll see why that answer has to have this form. If we have a plane ax plus by plus cz plus d equals 0, and we have some point at x naught, y naught, z naught, then this particular distance, this functional, will give us the distance d between that point and that plane. And we'll see why that's going to be the case. Okay, let's go into these notes with a little bit more detail. If we are given a point and a vector, we can define a line. We simply start at that point and direct ourselves along in the direction of this vector, and all scalar multiples of this vector will then trace out a sequence of points which gives us the locus of a line. Right, keep in mind the vector itself doesn't really have a starting location, not unless we define it as such. We're dealing with vectors as simply having magnitude and direction. That doesn't include a starting point. But once we give it a starting point, this actually determines a line. Now, parameterizing that line means writing it in this way, where we have a parameter called t, whose value is allowed to vary, and positive multiples of t will take us along the vector in a certain direction, and then negative multiples of t would take us along the other direction. Now, explicitly, we could take these coordinates, x, y, and z, and just write out their coordinate equations. And this is true even if we are directed in a way such that either A, B, or C, but not all of them simultaneously, is going to be non-zero. Now, it could be that at most 2 of them are non-zero. If 3 of them were non-zero, we would just have a point. It wouldn't go anywhere. It wouldn't be a line. But if at least 1 of them is non-zero, then it tells us how one of the coordinates, or 2, or maybe all 3, change as you vary this parameter t. Now, if one of them is 0, like for example, say the z coordinate, like let's say c was equal to 0, well then instead of having a equation here, you would just have the constant z naught. And it would tell you that this line, defined by the x and y coordinates change, would be somewhere in the plane z equals z naught. Z equals z naught defines an entire level surface in which would dwell our line. And there are similar kinds of parallelity or containedness that go into having the other combinations of A, B, C be equal to 0. For example, if I said A and B were both equal to 0, well then this would be this would be normal to, or perpendicular to, the xy plane. Right, x and y would have some fixed constant, and it would be oriented straight up out of the xy plane, our line. So the line would be normal to that. But we couldn't write it then in completely symmetric form, which is this, right? If they're all non-zero, we could solve for t in each equation and write this chain of equalities out, called the symmetric form of the line. Now, if z was equal to z naught, if, as before, this was a constant because c was 0, well then we don't have one of these equations, so we don't get one of these equalities, right? This equality would be gone. Instead, you would just have this fact that z was equal to z naught everywhere on the line. So let's do an example. If I have a line through this point parallel to this vector, I just use my definitions and write this out. This is 0 plus 3t, or 3t. This is 1 plus negative 4 times t, or just 1 minus 4 times t. And our z here is going to be 2 plus 5t. Similarly, in symmetric form, you would have the following. So a point and vector is very similar to defining a line by giving the point and slope. But now, we're in 3-dimensional space, so we need more than just slope to determine what the direction of our line is going to be. In the plane, we only need slope to define direction. So now, in the same way that in R2, you just need 2 points to determine a line, actually in any number of dimensions, you only need 2 points to determine a line. So say I had these 2 points. We'll call them x0, y0, z0, and x1, y1, z1. Well, we can just go through the entire previous steps with a vector if we have a single one of these points. We'll just pick P, for example. And a vector, say the vector directed from P to Q. We could also use the thing from Q to P, or we could use Q as our starting point. Both of those might give you different equations, but those equations would be equal to the same line. That is to say, where would they be equal to each other? Everywhere. They would trace out the same locus in space. They give equivalent lines, as I call them here. So here's another example for 2 points, right? We take their difference to define a vector. We pick one of the points, and we plug in. It's that simple. I'll let you pause it and contemplate that if you'd like. So note that in the above example, I have made 2 of the points match, right? So that z is a constant. We do get a 0 times t here. It's just a z equals 3. So that defines sort of a plane of xy points at the height 3. All the xy values in a plane such that z value is 3 is a plane, right? And this vector, this line, well, the vector qp or pq, yes, but also the whole line lies inside of that plane. In terms of your parametric equations, it would look like this. In terms of the symmetric equations, I would probably just write something like this without the chain of equality to z, and then just write the z equals constant line separately. That would be how I would write it. Now, note that if I rearrange this one here, multiply, do a little switchy, we can find out the equation for this line. Now, this line seems like a two-dimensional thing. And that's because we've confined ourselves, as an extra piece of information, we've confined ourselves to the z equals 3 plane. Or you could think of it as a projection. I say, which is the equation of the line if we had projected it into the xy plane. That's also true. But I think it's better, sorry, past Sean. I think it's better to consider it where it lies as a denizen of the z equals 3 plane. And not bother with projection at all. Not necessary. So now let's take a look at an application of the cross product. Remember that cross products have to do with sines of angles between 2 vectors. And notice that this value d is the sine of this right triangle here, made with theta, the angle between vector pq, and u, which I have as the vector directed along the line segment. So say you have P a point on a line, Q a point not on the line, and you take the line that is directed along U, and the distance here is going to be the magnitude of PQ, that's the hypotenuse, times the sine of theta. And we know that the product of this magnitude times the sine of theta is the magnitude of the dot product. Note here I haven't used abs vals, I've used the full double bar because this is a vector. So I'm talking about its magnitude. And rearranging to solve for PQ sine theta, that gives us a formula involving the cross product and the norm of the vector along this axis, the magnitude of this vector, also called its norm, that we could solve. Now it's just plug and play. Now we have a formula. So say I have a point, 1, 2, 3. Say I have my line again, given in parametric form by x equals 3t, y equals 1 minus 4t, and z equals 2 plus 5t. Well, how far away is that point? Okay, well, first of all, take your starting location where t equals 0. That's 0, 1, 2. Find the magnitude, well, better yet, find the vector form, of PQ. by taking the differences between Q and P component-wise. And then we get this vector, 1, 1, 1. Now we do the cross product. There it is, in vector form, 9, -2, -7. And if I then plug everything we know into this formula, what is the magnitude of U? It's the square root of the sum of its squares. Same thing with the magnitude of its cross product with PQ. That's the magnitude of the sum of the squares. Well, the square root, excuse me. The square root of the sum of the squares. And you get something like this. In general, you know, when we deal with distances in any number of dimensions bigger than, well, even I guess in one dimension, if I take the points truly at random, we're going to get irrational numbers. But even if I took rational points in 2 dimensions or higher, you're going to see radicals all the time. That's because of the square root in the Euclidean distance definition. So now let's talk a little bit about planes, right? If we have one line that is through a point parallel to a vector, we have one plane which is through one point, containing one point, and orthogonal to that vector. In fact, any vector from that point in that plane is going to be orthogonal to the normal vector, the one that's coming right out. This is supposed to indicate sort of a chain of, you know, right angle symbols right here. So that's going to have this equation. If we have the vector pointing straight out, ABC, and a point x naught, y naught, z naught, then we're going to have the following form. Now, why is that? Well, remember that any 2 vectors, including this black one and any gray one in the plane here, any of those vectors, so are going to have a dot product equal to 0 because they are orthogonal to each other. That was a property we saw of dot products, where if you have 2 orthogonal vectors, their dot product is always 0, right? The cosine of 90 degrees is always 0. And we could make a vector, give me any other point in the plane, Q, and I can make a PQ vector out of it. So let's take any other point in the plane. Let's show what it means for PQ and V to be orthogonal. Well, PQ is the Q component minus the P component, something like this, and we're dot producting them, and that's equal to 0. But what is that dot product? Precisely the equation of the plane, right? It's a quick proof. It just really quick. So notice that we do have like some parentheses here. I could distribute A, B, and C to these x naught, y naught, z naught differences, and then regroup, and we would wind up with ax plus by plus cz plus this constant d, where d is equal to the negative of the sum of sort of a dot product going on here. But I'll just say it's the sum of the pairwise product of the 2 lists of numbers, because x naught, y naught, z naught was technically not a vector. That was a point. But we are doing a very dot product-y thing here, I think you'd agree. So given 2 vectors, right? Given 2 vectors, let's say u and v, and a point in the plane, well, and a point, just any point. Now we can define a plane if those 2 vectors are actually not just like scalar multiples of each other. If they are scalar multiples of each other, and they're not the 0 vector, well, that defines a line. But a whole plane? Well, if the 2 vectors lie in that plane and they're not scalar multiples of each other, there's only one plane that fits the bill. Now, how do we find the equation for that plane? Well, we need to find the normal vector. And fortunately for us, we know a good candidate. We know that if we take the cross product, we're going to get something which is orthogonal to the 2 vectors that went into the cross product. And that's going to give us our normal vector to proceed as before, right? To take the P and V that we had before and, you know, just write the equations down the exact same way, now that we have a normal vector pointing out of the plane. And exactly the same way as before, if we have 3 points. Well, come on, just take one pairwise difference of points to be equal to your one vector. Likewise, pick P and R and make a vector out of that to be your second vector, and then just proceed as in this example. So we have point and normal vector, we have point and two vectors in the plane, and we have 3 points, all of which determine a unique plane. So let's do an example like that. If we take these 3 points, we define vectors from the differences of P and Q and P and R, just like this. We get these 2 vectors. We take their cross product. The cross product, 9, 6, 12, we could choose to be A, B, and C. Technically, I think it would be fine to factor a 3 out of that and just use the 3, 2, 4 that would go here. But this is all right. This is totally fine. You'll also get to that step down here. So notice that I put my 9, 6, and 12 here. I pick any one of these points I like, and I plug it in here as -2, -1, -1. And then we distribute and regroup. Factoring, I could take that 3 out now, and we still get the equivalent version of this plane. Both of these are redundant equations. They both define the same plane. There's, maybe a preference in smallness over the reduced version. Now, in a plane, there's only 3 things that could happen between 2 lines. Either 2 lines are parallel and they don't intersect. Either 2 lines are coincidental and they're the same line actually and they intersect everywhere. Or, and that's the 2 ways they could be parallel, or they're not parallel, in which case they intersect at a single point. This is, of course, in flat space. Now, in 3-dimensional space, we have one more option. Maybe they're not parallel to each other, but maybe they don't lie necessarily in the these 2 lines, anyway. They're not vectors, I'm talking about lines here. Maybe these 2 lines don't lie on the same plane. They could be skew. One could pass over the other without intersecting it because there's space in R3 to do this kind of thing. So we have a new option, a new answer to the question about consistency of a system of linear equations that went into defining these loci. On the other hand, if I have a plane and a line, they could coincide, they could intersect at a point, or they could be parallel in some sense to one another. Now, there's actually a whole plane of parallel points, and any line in that plane would be parallel to this plane. So it's not just that there's even one parallel line to this plane. Same thing with parallel lines. We could have them be parallel, but actually there's a whole bunch of different ways that 2 lines could be parallel to one another. There's not just a single 1-parameter family of parallel lines the way there is in 2D. Now for 2 planes, we have options. They could be coincidental, lying inside each other. Then they are just one plane, actually. They could crisscross and intersect in a line, or they could be parallel to each other and not intersect at all. And although these 2, I think, are pretty self-explanatory, I think this one requires a little bit more thought. We'll come back to that in a moment, I think. Let's first of all talk about the intersection of 2 lines, and then we'll talk more about this intersection of 2 planes. I'm sorry, there's also usually a really nice breakdown you can do at this point about intersections of 3 planes, which is also really cool. I'm going to have to skip that for now, unfortunately. You can get all sorts of ways in which they either generically intersect at a single point, or that they don't, or that they failed to, or that their lines are skewed to one another, their lines of intersection. But I digress. So intersection of 2 lines. So I'm going to use L and L prime and say, this is one line, this is the other. So just a subtle change of coordinates. I didn't want to use different subscripts. I'll just use primes. Has nothing to do with the derivative here. And if we equate these 2 systems of equations, we just set the x's equal to the x's and rearrange, we get something like this. Now, if this system in the variables t and s, notice we have 3 equations, 2 unknowns. That's an overdetermined system. So there's going to be some redundancy here, or it's going to be inconsistent. Now, if they have one solution, these lines intersect at a point. We can solve for that point. We could solve for s and t that would give us equivalence of this, that would solve this system, and then plug those back in where they would have to give us the same x, y, z. That's the definition of equality that went in here, and we would find that point. On the other hand, they might have infinitely many lines. These might be the same line after all, just with slightly different words, a different starting point, a different parameter, but maybe A, B, and C were actually the same the whole way, right? And they could have no solutions if they're either parallel or skew. So if they do not have any solutions, well, first of all, if they coincide, then A, B, C, and A prime, B prime, C prime have to be the same, or they have to be scalar multiples of each other. They have to trace out the same direction by some scalar multiple if they're going to coincide. Now, they could, however, also be equal to scalar multiples of each other and be parallel. If they are not scalar, then they go in the same direction. They're not coinciding, they're just going in the same direction, and they would be parallel. If they cannot be written, if you write these two equations down and you cannot write them as a scalar multiple of the other, you can't factor out something and get one equal to the other, well, then they cannot be parallel, and they are what we call skew. And this is how you would determine if a line was skew or parallel. Okay, let's talk about the intersection of two planes. I actually looked up a proof for this in Euclid, and it got torn apart on the internet because apparently it had gaps. I'm going to give a very hand-wavy proof, but I think it works pretty nicely if you can buy that you're allowed to sort of rotate our point of view in the coordinate system, and if I do so and I look at two planes, whatever their intersection was before, it's not going to change the kind of locus that it is before and after, just because I look at it from a different angle. So if we take two planes and we sort of rotate and translate ourselves appropriately, we could consider one of those planes to be the xy plane. That is to say, the plane z equals 0, the entire xy plane. And then the other plane is going to have some numbers to it. Ax plus by plus cz plus d equals 0. That's the hand-wavy step. By rotating the camera, we don't change the geometry of the intersection of the two planes, whatever that is. We're trying to prove it's a line. Let us say that they are not parallel, right? Let us say that they are, in fact, not parallel to one another and not coincidental. So they have two different normal vectors. They are somewhat at odds with each other. They have to intersect somewhere, and they don't intersect everywhere. Hence, either A or B is non-zero. Why do I say this? So we have one plane that we fixed to z equals 0. That's the xy plane. And we have another plane which cuts it in a way that is, its normal vector has this form A, B, C. And if A and B were 0, then you would just have a normal vector which is pointed only in the z direction. If that's the case, you're parallel to the original plane, whose unit normal vector might be 0, 0, 1. So, back to the proof. Because they are not parallel, x and y both can't have a 0 coefficient. One of them has to be non-zero. And what that means is, if I plug in z equals 0 as the part of the intersection, right? We let z equals 0, the sort of the defining feature of this plane, go into this equation for this plane. That's where they'll both be equal, is when their locuses agree with each other. Then we get something ax plus by plus d. But confined to the xy plane, what is that? That is a line. right? That is, in fact, the line. We could bring this over, minus the x over, divide by b, and we'd have this thing in slope-intercept form. So, in fact, then what we get when we plug in z equals 0 is the locus of a line. And so by the generality of our example, any two non-parallel planes will intersect in a line. So looking at this line, right, if we sort of look down the barrel of the x, right, direct your vision down this blue axis, and what you'll see is the intersection between the two planes, theta. But going forward by 90 and then theta, or forward by 90 and then theta, right, the normals are also going to have an angle of theta between them. Right, that's because they're both kind of shifted forward by 90 degrees from the parallel line of this projection, P2 and P1 here. Of course, we're looking down the planes, right? But still, we haven't talked about what is an angle between the planes, right? We've talked about an angle between vectors, but now we sort of have a sense of it. If we just sort of look down the slope, the line of intersection, we project that towards us, then we get two lines that have an angle theta, and shifting forward by 90 degrees doesn't change the difference of theta. So that means that we can find the angle between the planes just by finding the angle between the normals. And that we can just rearrange the dot product for. Here's an example. Let's say I have two planes. Find their normal vectors. Do we want another angle? Find their magnitudes, which we can do easily. Find their dot product. Oh, hey, these happen to have dot product 0. They must have been at 90 degrees to each other. In other words, the angle is pi over 2. Now, we can find the locus of their intersection, right? We find their angle, and we can find also their line of intersection. How do we do that? Well, let's take P1 and minus P2 from that, and we get a system of equations that will cancel the z character and let us solve for x in terms of y. Likewise, if I take this linear combination of these two equations, P1 plus 4 times P2, that will cancel the y's from each other. We're doing elimination here. And then we've eliminated the y variable, and we have x in terms of z. Now, just rewriting that, right, that x itself, so minus 0 divided by 1, is equal to this thing involving y, and that is equal to this thing involving z. Well, hey, this is the symmetric form of a line. And from that, we can extract the parametric form of the line if we so choose. As a final sort of example, let's look at the distance between a point and a plane. So we can find the distance between a point Q and a plane if we have its normal vector and a point on that plane. So from what we can do here is we can take P and go in the normal vector n, go up from that. And then notice that we also then, if we go from P to Q, we get this kind of right angle system. If I project down this way, if I project PQ down onto this line of n, onto this vector, the normal vector n, then what I get is another vector. And that vector has a certain length. And that length is precisely, I mean, we're all inside this quadrilateral here. That length here, d, is going to be the length of that projected vector. Okay, so then we just take the magnitude of that projected vector. What's that? Well, the projected vector is going to be, well, we actually have an equation that goes straight to the magnitude, right? The component, if you will. And that was the magnitude of the dot product. I should have a hat over it. Divided by the magnitude of n itself. So let's say we have a point, Q. And we have this plane, 3x minus 2y plus z equals 0. So notice that if I just choose them all to be 0, that is a point in the plane. So 0, 0, 0 is in the plane. And so the question is, how close is Q to the plane? Well, it's not the distance necessarily from P to Q. You know, it might be shorter than that, right? It might, in the same way that this D is shorter than the length of PQ. So what we do is we take the vector PQ, 1, 2, 3, and we find the normal of the plane, 3 minus 2, 1. We take their dot product, we get 2. We find the norm of the normal vector. Sorry. Yeah, the norm of the normal vector. That's fine. The magnitude of the vector orthogonal to the plane. And we get the square root of 14. So D is just their ratio. That's it. That's all you have to do. Here is an application of that. If you have two planes, you can find the distance between them, right? Minimizing the distance between the two planes that are parallel to one another. So let's say we have two parallel planes. How do I know these two are parallel? Well, look at their x, y, and z components. They're off by a scalar multiple of each other, right? Namely, this is n1 times -2 would get you n2. Right, there, I said it. Now, find a point on each plane. So take 0 for x and for y and z, right? Just zero these out. There'll be 0 somewhere. And then ask yourself, well, where is x going to have a right value in order to, still be on the plane? And this is something you can do as long as the coefficients aren't themselves 0. Is you can let two of the variables be 0 and then solve for the third. So if we do that in P1 for x, we're going to get, minusing this over and dividing by 2, we get -2. Minusing this over, divided by -4, we get +4. Or sorry, +2. So here are 2 points, one on each plane. And then we can use that as the point in a plane and the point off the plane to find D. So just taking PQ, this vector, we get 4, 0, 0. And then taking its dot product with PQ and the normal vector of the first plane, we get 8. The magnitude of the normal vector of the first plane is the square root of 29. And so D is just their quotient. Here is some praxis for you to think about yourself. Try these on your own. First, find an equation passing through a point and parallel to another line. See if you can extract the vector that would have gone into this. Then try finding the angle between two planes. Then try finding the distance between a point and a line and a point and a plane. Good luck with your studies, and I hope to make another video for you as soon as I can.